All right, cool. Excuse me. So there are a couple homework questions. Let me share my screen here and let's look at those. Make sure my speakers are working as well. So there are a couple questions from the limits at infinity homework. Where my approach to teaching this, there are kind of different ways to teach this material. My approach was to focus on polynomials, specifically in the notes. And this question you can see is asking about an exponential. And so take a look at that one. Is that large enough? That seems okay. So this particular function, I don't know if you can see it. Maybe I'll just write it bigger at the top of the page here. It's 4e to the minus 0.1t plus 5. And I think everyone gets a different one generated, but it's going to be some e to the minus something. And there's kind of a key concept, which is when the denominator of fractions gets bigger, it eventually, that fraction gets smaller and smaller, right? So like, I guess what I'd say is notice how 1 over 1 is bigger than 1/2, which is bigger than 1/3, right? As you make the denominator bigger and bigger, the fraction's just getting closer and closer to 0, right? And so in other words, if we do the limit as x goes to infinity of 1 over x to the n, that's going to be 0. Or we could say that's the same thing as the limit as t goes to infinity of 1 over e to the t. Right? It's the same concept there because you're making the denominator bigger and bigger and bigger, and so the fraction gets smaller and smaller and smaller. And so those limits go to 0. Depending on, I'm actually teaching a calculus course at another university online right now, and that textbook goes into this a little more in depth. And for whatever reason, we're just kind of not going to depth on this particular type of limit. But it doesn't come into play here, and I like going over this one in class, and I like putting a couple in the homework that extend what we talk about in class. And I know that's frustrating sometimes because maybe you feel like, oh, this isn't in the notes. And sometimes I get annoyed emails that are like, why didn't we cover this? And they're extensions. It's not like we didn't talk about this stuff. It's that you need to think about it in a different context. And so let's look at this one in this context then. And so just notice, I guess the thing to notice here is that we can't use the info from the notes because this function for e to the minus 0.1t is not a polynomial. Right? It's not we don't have a rational function here. So instead, we're going to use this idea of 1 over e to the t going to infinity is going to eventually be 0. Or we can think it, and I'll point out a couple different ways we can think about this one. And please stop me if this doesn't make sense. And so I'm going to talk about maybe 3 options on how to solve this one. Do I have room to put it in here? I'm probably just going to have to start writing over top here. So here are my options for solving this one. Number 1, let's just do it. Let's just do the straight limit. So the limit as t goes to infinity of 4e to the minus 0.1t plus 5. I guess maybe the thing that people are missing too is what happens when you have a negative exponent? It turns into a fraction, right? When you have negative e to the minus t, that becomes 1 over e to the t. Maybe I took that for granted and that people are missing that. I'm not sure, but remember this, right? This becomes that. Right, so the denominator is going to get bigger and bigger and bigger, just like we had a second ago. And so this piece right here is going to go to 0 as t goes to infinity. Does that make sense? And so then this answer just ends up being, when we evaluate the limit, this is 0 plus 5, which is just 5. All right, so when t goes to infinity, it makes that fraction go to 0. Questions about that? We did see this in the notes a little bit because we looked at the infinite limits of 1 over x, for example, which is similar to this one. I usually do this one in class. So I usually wait till someone brings it up and talk about it. So no problem there. Questions about that one? What I'm trying to say there at all? The other way to sort of think about this, if that didn't appeal to you, we did talk about other ways to do this, right? We did talk about option 2 that I'll mention, which is to graph it, right? We've spent a lot of time in class. We could graph this thing and also look at the limit that way. And this is the kind of function that if you took pre-calculus with me, you should know how to graph this function, right? It's an e to the minus x function that's been stretched vertically by 4 and moved up by 5. And so I don't even need a graphing calculator because I've taken pre-calculus and I've taught pre-calculus, and I know that this is going to look something like this. Instead of going up, it's going to be going down towards that. What color should I use? Maybe yellow. Kind of does this. And that point right there is at y equals 5. Right, so way off onto the infinite limit, it's going to approach 5. So we talked about graphing it. The third thing we talked about doing in the notes, if you can't figure this out by hand, is we could always make a table, right? So the third part of this is we could make a table. Right, we just plug in some x values that get big, like 10, 100, 1,000, etc., and you plug them into the function. Except that should be t values, sorry. And you'd see they get they don't get big. What I meant is they approach 2 or 5. So there's 3 sort of options to think through this one. Again, it's an extension of a little bit of what we did in the notes, not something exactly like it. So thank you for bringing that one up. But hopefully that makes sense based on some of the stuff that we know. Is everyone okay? Questions about that?
I just have a question, actually, just a clarification.
Yep.
So why is the e to the negative 0.1t go to the denominator again?
Oh, and thank you for bringing it up. It should, so I actually, can someone correct that? It should be when you put it in the denominator, it makes it positive. So let me delete that. I just deleted the negative sign right here. Because, where can I squeeze this in? I'll try to do it right here, right? If you had like x to the, x to the minus 1 equals 1 over x, right? When you have like x to a minus power, you make it positive by putting it in the denominator.
Oh, okay.
Is it Tommy asking that? Remember that from pre-calc?
Yeah, that makes sense now. That's one of the...
That's how we get rid of negative exponents, right? We never want to have negative exponents in a problem. And so if you have a negative exponent, you get rid of it by moving it down. And in this case, moving it down helped us see that it goes away. And does everyone see that thing I highlighted right here? Let me just highlight it again because I forgot to get rid of it when I moved it down. Right? It's let's see here. It's negative right here, and I made it positive by moving it into the denominator. Is that right? Any other questions about this one? All right, I'm going to save this one. Let's see here, save to files. If I just send it to PDF Expert, I think that's good. And then what I'm going to do is I'm going to put these in our shared Google Drive folder so you can look at it later. The other question that someone asked about was number 3, and I'm glad this one was brought up too. Again, yours might look a little bit different. Let me just try sending this right over to PDF Expert just to begin with. Because then it'll be a little bit bigger. So notice how it's like it wants you to do multiple things. It's saying answers separated by commas. And so that means we're looking in both directions. We want to do the infinite limit to the right and to the left. And so there's a small caveat to this one, and I think maybe Simon is the one who asked about this the other day. I can't remember. but we want to look at this and the other direction, right? Minus infinity, like what happens on the outsides. And so graphing, it's a nice way to do it if we had a graphing calculator, but let's just think it through. And so when we do this, the biggest power on the top and the bottom is a 3, right? So the degree in the top is 3, and that's the same thing as the degree in the bottom. And so when we do both these limits, what really is going to matter are the two leading terms. Let me just pull those two things right out here, right? So we really care about 3x cubed over minus 10x cubed, right? Because those are the ones that have the biggest powers, and so those are what's going to control what happens in the long run. Does that make sense, right? That's what we learned in the class the other day. Is that part okay? And so I already have used too much space, so let me just make this. That's not what I wanted to do. Let me do this again. I think I can do this, and I think, can I make that smaller? Can I I guess I can just move it, but that's not very helpful. All right, I'm just going to go with it. So so as x goes to infinity, since the powers are the same, this thing, you just use the coefficients, right? It's going to go to 3 over minus 10. And so that's one of the horizontal asymptotes, is at minus 3/10. And someone had asked the other day, like, oh, does it matter if you're going to positive or negative infinity? And I was like, oh, I can't really think of a time when it would. And it occurred to me later that I was wrong about that. And actually, it kind of comes up in here, although it sort of also doesn't really matter here as well. So, but notice how if you plug in negative numbers into something being cubed, they stay negative, right? Like, in other words, minus 1,000 cubed, the negative sign doesn't go away. And so when we do the negative limit, as x goes to negative infinity, those two values are both staying negative. This is going to go to, sorry, those should be cubes. So we're going to have the 3 over minus 10, right? And then we're going to have a negative over a negative, because those two things are both negative, and then they just happen to cancel out in this case. And so we're still going to get minus 3/10. But the reason that what I'm trying to say here, though, is if it was like x squared over x cubed, and we were going to negative infinity, this one's going to be negative when we do that, and so it's going to make it a negative value. And so we do need to be a little bit careful about that. I think this is the only case where that comes up in this particular homework. And so it wants us to enter these answers separated by commas. So we would enter those, come on, in here, and we would just do minus 3/10, comma, minus 3/10.
You just go down just a bit, if you don't mind.
Did you say scroll down?
Yeah.
I don't think I can scroll. This is just the size of it's just filling up the page.
Oh, really?
Maybe if I do that.
Yeah, perfect. Thank you.
I was gonna say something. Oh, everything we did in the notes, we always kind of verified it with a graph. And so it's a great idea to think through this algebraically, but pulling up a graph on Wolfram, like I showed you how to do, is a great way to just see what's going on and see that you have that correct answer.
Could you please repeat that, please?
Repeat what? I've been talking for a while.
Well, the two answers, like the second answer, basically.
So when you're plugging in negative values and you raise them to a negative or an odd power, they stay negative. Can I let go of the screen now? Is it whatever written? What was that? Right. So like this thing right here, right? Minus, when you raise minus 1,000 cubed, it stays negative. And so what I'm trying to say is, if you're doing a negative limit and you have odd powers, then that's going to create a negative number. But in this particular case, they just cancel each other out because it's on the top and the bottom. And so you end up with the same horizontal asymptote. So I don't, do people know what I'm talking about when I say horizontal asymptote? This is what we talked about in the last class period. And if you haven't started this homework, you might be lost. So, which is one of the reasons why you should start the homework before, it's due tonight and we're talking about it in class. So it's nice to be able to follow along with this stuff. I don't know, is that what you wanted me to repeat, or I'm not really sure if this is helpful. Have you started this homework? I wasn't sure who asked that.
Yeah, I did start it. I did watch the video.
So watching the video is different than starting it. Have you looked into these problems?
Yeah, I've looked into the problems. They actually kind of do make sense, but when I did try to do on number 3, I got the first answer, but I still just didn't understand how to get the second answer.
So my guess is in your problem, and I'm going to pull yours up just to verify this, but it's just going to be the same limit repeated because it's going to cancel itself out. So you should just enter the same thing twice, separated with a comma. Let me just verify that that's true. Yeah, I think you actually have the same problem, or very close to the same, almost the same problem. No, it's actually slightly different. But you have the correct answer. You just need to enter it twice, separated by a comma. Janetta. Can I answer some other questions about this one? So I'm also going to, obviously it's in the video, but I'm gonna put this in our shared folder. Let me just show you that. All right, so let's see here. How do I do that? And let's see, I had a second one. Where's that other one that I sent in here? Not that one. This one? Yeah, let me put this one in there too. Come on. Oh, this happened last time. I may have to figure out how to do this later. Anyway, I'm just trying to show you, it's in our Dropbox, right? If you go to our Dropbox, there's a homework solution folder, and I'm trying to put all these in there for you to look at later. I'm gonna get started with the notes. Are there other sort of general things that people want to look at before I do that? Okay, we're talking about rates of change. Maybe while we're here, I'll just mention the weekly schedule. I'll just remind you of a couple things. So there's homework due tonight, right? We've got our web work assignment due this evening. And please keep in mind that there's a second thing that you need to submit to Gradescope that's clearly explained here. It's also clearly explained on web work. If you haven't seen that yet, let me know if you have questions. We're working towards a test next week. So we've got a test next Friday. I've got lots of stuff posted on Blackboard for that. Questions, review stuff, all kinds of things. And we'll do a quiz in class on Friday. We're going to do a quiz on the homework that was due last week. And I'm probably going to ask a basic continuity question, but it's open notes. If you have all your notes in your homework, it should be no problem. All right, let's look at this. So here we are talking about rates of change, right? We've moved out of limits. We kind of finished our limit discussion with the soybean problem. And we can continue looking at homework questions, but the point is we're using limits now to build things like rates of change. So that's where we are. And in this particular section, we're talking about 2 different types of rates of change. And that's one of the major topics of calculus is derivatives, which is a rate of change. And so let's dig into it. Okay, so oftentimes, and this is important because of what it says at the top here. I'm just going to kind of paraphrase what it says right there, but generally when we're modeling things, and I do mathematical modeling in my own work, we often want to like think about what's going to happen in the future, right? Like we think about how many cases of coronavirus are there going to be next week, right? Or we care about polar bears or something. We want to know how many polar bears are going to be in 10 years or whatever it is, right? We want to know something that we usually project into the future. Well, what that usually involves then is thinking about how the system is changing and then projecting that change forward. And in calculus, we think about changes as derivatives. And so that's what we're at right here. And we're going to talk about two different types of rates of change, right? And so the first type here are all type A. I'm going to highlight those all in green because those are all similar to each other. In the first instance, you could think about two different ways a moose's weight changes, for example. Let's say we're a moose researcher. You might care about how much weight is gained over the first 10 years of its life. That's a different kind of rate of change than type B, right? Which is how's the weight of the moose changing exactly when it's 200 hours old, right? One sort of over a long period, one's at a very specific moment. The second thing is talking about how is the concentration of a drug in a person's blood stream changing. We might care about that changing. How does it change over the first couple hours after ingesting it? Or maybe we care at a very specific moment, like 25 minutes after taking the drug, right? Or the third example maybe I'll share is this is out of a textbook that was talking about federal spending on stem cell research. If we care about long-term kind of general changes, we might care, well, how has it changed over the last 10 years? If we're hyper-focused on what's happening right now, we might care about what's happening in 2007 or 2021 or the specific year we care about. Now, each one of these things, each one of these examples, these specific examples is kind of contrasting something over a period compared to something at a specific moment, right? And so that's getting at these two different types of rates of change. Type 1 above, or type A, I should say, those are all what we call average rates of change. And you can see, like it says in the description, this is sort of talking about what happens on average, right? It happens over a period rather than what happens at a specific moment. So let's dig into the moose example. And I get some of these examples from this textbook I used to teach out of that talks a lot about biological examples. And so they had a function in there that was talking about how much weight a moose, or how much a moose weighs, I should say. And one of the things they were saying is a male moose might gain 500 pounds in the first 5 years of life. Oh, sorry, in the first 5 years of life. How much weight do they gain on average per year? Right, that's the question of the average rate of change. I feel like anyone can answer that, and I would love to hear someone chime in. How much weight do they gain per year?
100 pounds.
100.
100, yeah, thank you. A couple of people answering, that's wonderful, right? 5 years, 500 pounds. Really easy just to set up, well, they gained 500 pounds in 5 years. That's very easily 100 pounds per year. Right, so that's just an example of an average rate of change. Now, again, it's over like 5 years, and so we're not saying every year they gain exactly 100 pounds. They probably didn't gain exactly 100 pounds any year, right? And there may be places where they gained a lot of weight. They may have lost some weight over that time. They probably did, right? Most mammals lose weight over the winter, for example. Well, not us mammals, but most mammals that live in the wild lose weight over the winter, right? So they might go up, go down a little bit, go up, go down throughout the 5 years. And we're just saying, like, on average, over that span, they gained 100 pounds per year, right? So you're gaining general information, nothing very specific. Let's contrast that with type B, right? Type B, and maybe I should use a different color. I'm going to go back up here and use blue just so we can write in blue. It's not easy to, oh, maybe purple's fine. Can't really write in purple or yellow ink. So anyway, all those type B things up the top there, that's what we would call instantaneous rate of change. And in calculus, we refer to those as derivatives. So that's, we're building towards this word called derivative. Or we're actually going to introduce it right now. But the point is, these things are happening at an instance. Okay, it's happening not what is the moose gain over 5 years, what's happening right now, right? And so maybe an example of that in terms of this moose thing would be, you know, at 65 days old, that's still a baby moose, right? Yeah, a baby moose is gaining, let's say, oops, that's not gaining. I'm just totally making this up. 5 pounds per day. So again, that's like hyper specific on the 65th day, how much pounds are they going to gain? Now this is really, really specific. And so you wouldn't want to use this information on day 70, for example. This is just applicable to day 65. Now it tells you what might happen in day 70, right? Like in day 70, we might expect this thing to be 20 pounds bigger or so, but we're not getting exact results there, right? We get some very specific things on a day, not sort of anything around that day. Someone say something in the chat here. Oops. Oh, let's see this question that Simon asked a little while ago. I'm sorry, Simon. Maybe we can get to that towards the end here. Question about the difference between those two things. See what I'm saying there about how one's over a period, one's hyper specific, right? One sort of gives you general information over a time span. One's very, very specific. The thing that we're eventually getting into here is the instantaneous rate of change. As I mentioned, that's a derivative. That's one of the main focuses of calculus is this concept of a derivative. And I'm going to highlight the part that's relevant to us in calculus. We represent that with this notation F apostrophe with a point at A, right? So this thing that I'm highlighting, F prime of A, is one way to say that, or the derivative of the function at A. That's telling us how the function is changing right at that very point A. Okay, and I'm going to draw some pictures to kind of illustrate this concept over the next couple of periods. Questions so far? Questions at all? Okay. So you can look on the next couple of pages. Let me just monitor the chat. I should have the chat up here just in case something happens with that. Over the next couple of pages, we're going to dig into these two things, right? So, sorry, just getting distracted by my email. So on the first page, we're going to dig into average rates of change, right? So this is going to be the, did we use green on that one? Yeah, this is going to be the green stuff. And then on the second page, we'll dig into the instantaneous rate of change one, which is the purple stuff. So one thing at a time. I think my guess is we'll probably definitely get through this page. I don't expect to go too much farther than this. I'd like to ask you to try one at the end of class. And then I want to talk about taking attendance. I've had a hard time taking attendance in class, so I'm going to ask you with your help for that. Anyway, just kind of previewing what's happened here. So average rate of change, like I said, it's over a period. And so if we want to calculate average rate of change, it's very straightforwardly given by this formula, right? The average rate of change given by the function f of x over some interval x1, x2 is given by this, right? So it's either we're thinking about how the function changes divided by how the x values change, excuse me. And so there's three ways to look at that, right? This is sort of an intermediate notation. And the actual thing that we really care about is the last expression, right? We're plugging in the function values on the top. We're subtracting the function values on the x values on the bottom. I also just want to add, if you're not familiar with this, oops, with this notation, the triangle here. Does anyone know what that is? The triangle. So it's not a triangle; it's a Greek letter. I don't know what that one is.
Delta.
Changing.
Yeah, it's delta. So it means changing. Exactly. I didn't mean to put parentheses around that. Quotations mean. So the delta means change in, It's something you see in not just future math classes, but lots of science classes as well. It's a good thing to know. So the change in part is where you subtract the two values, right? If you want to know the change from x1 to x2, you subtract x1 minus x2. So what else does that look like, right? This should kind of look familiar, like something that you see in previous classes. I know I harp on pre-calc a lot. We see this in pre-calc, but we see it in lots of other places too. What is that?
The slope formula, right?
Yeah, that's a slope formula, right? That's the definition of the slope. But the slope of what specifically? The slope connecting two function values. So it's the definition of the slope of the line that connects f of x1 and f of x2. So we're going to draw a picture of this right now on the graph spot. But that's sort of what we're thinking about. All right, and that's why we get this average rate of change, because we're just like doing a slope between 2 points, and we're going to miss the intermediate parts. All right, so let's start drawing this. So let me set up my picture down here. So we care about two x values, x1 and x2. Let me draw the graph first, actually. Try to draw a graph that looks like this. So that goes up, down, and then kind of goes back up again. That's going to be our f of x. And then we care about two x values. And so let's label x1 and x2. I'm going to make x1 kind of on that hump right there. All right, so this right here is f of x1. And let's take x2 kind of farther down the line so that it lines up above that point. Right, so first of all, notice the x values are on the x-axis, of course, but the f of x values, those are y values, right? So f of x1, f of x2 are outputs. They're function outputs. They're on the y-axis. And so this thing that we're trying to do here, this formula that I'm circling, is just the slope connecting those two green dots on the line that I drew. All right, let me make those dots a little bit bigger so we don't lose them. Right, so this thing I'm trying to show right here, this line is literally what we're doing, right? We're just calculating the slope of that line. And kind of the key takeaway, the thing I'm trying to harp on, that I hope it's not too annoying, but I'm going to write it down one more time, is that we're not getting specific information about this, right? We're getting very general information. In fact, based on the picture I drew, the average rate of change would be positive, right? Because the slope is going up. But this graph went down in between them, right? This graph actually goes up, and then it goes down, and then it goes up again. But the average rate of change would only capture an increase because we're doing a general thing. So we don't get that in between information. We just get a general understanding of what happened, right? So note, we're not getting specific info. And I sometimes go back and forth about whether to write detailed stuff about this, because I know sometimes people don't write this stuff down, which is your choice. The reason I do is because when you go back and look at this later, it needs to make sense later, not just tomorrow, but a week from now when you're working on the homework, or 2 weeks when you're studying for the exam, etc. And if you just write this kind of stuff down, you'll be able to read this later. So we just get the general trend of overall change. Okay. All right, think about the moose weight example. This could be a function of the moose's weight. It goes up, it goes down, but overall it went up, and so we get that average rate of change. Questions about that at all? Okay. Let's do a couple examples. How are we doing on time? We're doing great. So let's do that moose example. So here's an example that's actually implementing what we just did a second ago, but with a function. So the weight of a female moose, it says right here, is given by this function, right? Where t is measured in years. Right, so we have a real function to work with. You plug in a t, it tells you the weight of this moose in kilograms. What's the average rate of change from 1 to 3? Right? How does it change overall? Again, it probably goes up and down in between there, but overall, what happens? Well, really easy just to implement this formula that we just used, right? So we'll do the average rate of change. I'll abbreviate rate of change occasionally, ROC, from t equals 1 to t equals 3. That's what we care about. Well, that's going to be the change in weight. I'm just trying to write the details out just one time. Change in weight from 1 to 3 over the change in time. Who's having a hard time seeing the bottom of the screen? Can you see everything I wrote right there? I think it was Josh. Does that seem okay? Okay, so the change in weight, we just plug those function values in, right? So we're going to do this kind of thing up here. We're just plugging the function values in. And so we're going to do W of 3 minus W of 1 over 3 minus 1, right? So on the top, we're plugging things into the function. On the bottom, we're just subtracting the inputs. And note, we want to have a unit here. So it's helpful to note that on the top, we have kilograms, and on the bottom, we have years. Because that just shows us that the unit's going to end up being kilograms per year. And so we just do these things, right? You plug those numbers in. When you plug in 3, you get 440.8. So moose will gain 440 pounds in 3 years. That's a lot. Female moose, at least. And then 2 years on the bottom. Real easy, right? And then you just do the subtraction, divide by 2. So on average, 48.8 kilograms per year. And this is a female moose, so maybe the male moose is closer to what I guessed. I don't know. Right? Did they lose weight throughout there? Probably. Were there years where they gained more than 48? Probably. Did they ever gain exactly 48.8? Probably not. But just overall average trend, that's what we looked at. It's okay.
Where'd you get those numbers in the numerator?
I plugged them into the function. So when we write down W of 3, W of 1, here's W of t. So you plug the numbers into W of t to get those. And I just did it ahead of time, right? So it's like 369 times 0.93 raised to the third times 3 to the 0.36.
Sounds
I
good.
should just plug it in t values. Other thoughts?
Isn't this kind of like y2 minus y1 over x2 over x1?
That's exactly right. Yeah. So that's what we were saying up here. This is literally just the definition of the slope of a line, which is exactly what you just said. Yep. That's exactly it, which is what I was trying to say in this picture, right? We're just calculating the slope of that red line. It's just connecting the 2 points. Yep. Keep the questions coming. That's great. Thank you for thinking about this. More stuff. All right, let me do one more example, and then I'm going to ask you to try the one at the bottom here. oftentimes people see this kind of thing when they're talking about average velocity. Like that's something that comes up a lot in physics. I don't know if you're taking this class because you want to take physics later, but if you do, you look at velocity a lot of times in physics, and just know that velocity is a type of rate of change. And so, and I think you know that, right? Like if I said, when you get in a car and you drive and I said, what's your velocity right now? You'd say, oh, well, it's 30 miles per hour, right? So miles per hour is your rate of change. And so I'm just trying to introduce right here this concept that we're just using the exact same thing again, right? It's just change in position over change in time. So change in the y values divided by change in the x values. But it just has specific applications that oftentimes come up. So for example, another really easy one, right? If we drove from Fitchburg to Philadelphia, which is approximately 300 miles, and it took us 5 hours, I think everyone could tell us approximately what our speed was, right? What was your, you told your mom that, and she said, what's your at? Whoa, wow, you were going on average blank. Everyone would just say, oh, well, you divide 300 by 5, and you get the average velocity. But just trying to bring it back to the context here, we're actually using this formula, right? So average velocity is change in position over change in time. That's supposed to be a triangle. The change in position, you went 300 miles, right? So 300 minus 0, you start at 0, you went to 300. That's miles. How long did it take? You went from 0 hours to 5 hours, right? And so it just ends up being 300 over 5. And again, I know everyone probably knew how to do that. I'm just trying to point out that you're actually using this formula when you do that. And we would say, oh, well, we drove 60 miles per hour. And I don't think anyone would claim that the entire time you were driving that fast, right? You start at 0, take some time to get to the highway, maybe you stop for coffee, whatever. But overall, you on average went 60 miles per hour, right? I hope that kind of illustrates the average rate of change concept there. All right, I'm gonna ask you to try the next one on your own. So are there questions about the formula or how it works, anything like that? I gotta get some different options in this room. Wanted to do like some breakout rooms. I don't see that option. I gotta fix some stuff. Maybe if I stop sharing, I can do breakout rooms. Let me see what happens. Nope, no such thing here. I gotta fix my options. Okay, let me share again. So I'm just gonna ask you to set this one up then and just think about it on your own. Shouldn't be that tough. This is another one that's got a cool application, I think. How do you get rid of that now? Like, where the heck did the search box come from?
If you click the little magnifying glass on top of it.
Thank you. Yeah. Well, I actually remember that because I spent a long time one time on some app trying to figure that out and ended up having to look it up. That was one of those embarrassing times for me. Okay, so this is an application. Everyone, I don't know if anyone's ever seen this function or this equation before. This is a very common kind of thing. You might see it again in a physics class. This describes a change in motion, in this case, height of an object. So you oftentimes see this in physics where it's like, oh, someone threw a ball off a roof and it's like going towards the ground or something like that. Anyway, so this particular function we're saying is telling us the height of a kingfisher, which is a type of bird, from the water t seconds after it dives. And so it's given by, the setup is given by this picture right here. Let me just hone in on this picture. Right, so this picture right here is sort of the situation. It's like we have water down here. Kingfisher is a type of bird that will start up top here, maybe in a branch, and then it'll like dive down into the water to fish. And so it might be on that trajectory and it's modeled by this equation. This is legitimate, like was what I'm trying to say. This isn't just some made up thing. This is real. And so we might want to know, how fast was that thing going over that time period? Wow, it like bolted into the water. How fast was that thing going? Well, we could calculate that. And so I'm going to ask you to use it, to try it using this function. And so if you know what you're doing, this makes sense, give it a go. If you want me to just keep talking for a second and set it up, then let's do that, right? So this tells you the height, right? H tells you the height at a given time. And so we want to use that. I don't know what I was going to say there. So we want to do average velocity. We want to do the change in position over the change in time. My goodness, I think I just clicked something on the right-hand side of the screen. Jeez, okay. Change in position over change in time. And H tells you the position, right? So you want to plug things in to the position formula, and we're doing it over the first 2 seconds. I should have mentioned that too, right? So that's from 0 to 2. So take a second and try that one. This should feel comfortable to you. This is the kind of stuff that's in the homework for next week, and is the kind of thing that's going to be on our first test. So let me just sort of continue slowly doing this one. All right, we want to do this. And it's somewhat easy to plug these numbers into this function, right? 2 squared is not too bad. There's no decimals or anything. So it ends up not being terrible. I'm just going to give everyone a minute to think about this one. And the thing I would like to also ask you is, there's going to be something weird about the sign. So it should be a negative number. You'll end up with a negative number. And why is it negative is the question I would pose. All right, I'm going to stop here and see if anyone has any questions. This is a real situation. I'd be walking around and see if there are questions. Tommy, you say something?
No, that was me.
Oh,
Just
John, what's up?
the numerator H2 minus H0, shouldn't the 2 be 20?
Shouldn't the 2 be 20? Is that what you said?
Yeah.
So we're trying to evaluate the velocity over the first 2 seconds. And so we want to, so 2 is the end second and 0 would be the starting second.
Yeah, but is the top's the position, so shouldn't the first number be 20 since it starts at 20?
So it's the change in position, right? So it went from, oh, I see what you're saying.
Yeah,
Wait, no, now I'm confused again.
it starts at 20 and then it dives down to 0.
Right, so that's the H of 0 time. Right?
I don't know. I'm just going to follow along.
So it starts at 20. That's correct. But we're trying to think about the overall change. And so, yes, it changed by 20 over that time period because it went from 20 down to 0. But that's not really how we're thinking about it. We're not trying to like look at the graph and calculate it. The graph is nice because it kind of paints the picture. We should just be taking these numbers and plugging it into the function. We want to
Would
see
it be
where were we
10?
at, we want to see where were we at 2 seconds, where were we at 0 seconds. Sorry, what was that?
I don't know if I'm right, but actually, no, let me just wait for everybody else.
Okay. Other thoughts before we keep going? I'm gonna plug those numbers in and see what happens. So when you plug a 2 in, you'll get
If you plug in 2, you'll get 0, right?
yeah, exactly. You'll get 0. You'll end up with 20 plus 20 minus 20 plus 20. So you get 0.
And if you plug in 0, you'll get 20.
Correct. So just like John said, we started at 20.
So it'll be 10, right?
Oh, I see. You're going for the answer. Sorry. Yeah. And then so we divide by 2 minus 0, and so that's 2, and so that's seconds. And so we end up with minus 10
Oh,
feet
minus
per
10.
second. And this is the thing I was trying to get at originally, and I was sort of trying to clarify with John a little bit, is if we just think about, oh, well, it's 20 on the top, we lose the negative sign, and that's actually something that means something here. So let me just pause and talk about the process and then the number -10. Is it okay reaching that before we interpret it? John, does that clarify what you were thinking about before at all?
Yeah.
or-
Yeah, I understand now how like it goes from like in a real like life sense how it goes from like 0 to 20 and how it's negative. Yeah. I get it.
Yeah, because it's going, and so maybe, I don't know if you know the answer to this, but, and Gregor got that too as well. Nice. What does the negative sign mean? Like, what's that telling us about this situation?
It's going down.
It's going down, yeah. So it's negative because the bird is going down or traveling down, whatever you want to say. So with velocity, there's usually a direction involved. And negative just means it's going from somewhere high to somewhere low. If it was like going from the water back up into the tree or something, it would be a positive value. So I'm just going to maybe add that little note at the bottom. Velocity. In velocity, so in velocity, the sign tells us direction. Usually positive means like forward or up. And usually negative means backwards or down. Like in the going to Philadelphia example, 60 was positive because we're sort of thinking about we're in Fitchburg and we're sort of moving towards Philadelphia. But if we went the other way, maybe it would be a negative 60 because it would be going backwards towards Fitchburg. Something like that. What do you think?
I have a question.
Yeah.
Philadelphia example.
Yep.
So you're going from Fitchburg to Philadelphia, you're starting from 0 to 300 miles, right?
Well, what I'm trying to say is it's that choice is relative, I would say.
What I'm confused is because you put like on the first example you say 300 minus 0, and on the second one 0 minus 20, but they're both starting from 0 and they're both going to a certain, you know.
So in the second example, they're starting at 20 actually, right? The bird's like in a tree or something and it's diving into the water.
Oh, okay.
They're on different planes. One's on the X, one's on the Y. So it's what makes
Yeah, and I wouldn't get too caught up in like, oh, should it be positive or negative? Just know that one means one direction and one means the other direction. And so, and in the Philadelphia example, which direction is forward and which direction is backwards is just relative, right? And what all I'm trying to say is if we're talking about going one way, we'd make sure it's positive, and we're talking about going the other way, we'd make sure it's negative. It makes more sense in the bird example because it's like, oh, well, it was high and then it went down, and that's a little more easy to interpret, I would say.
Thank you.
Yeah, good thoughts about that. Other questions like that? But I'll just reiterate it again because it's kind of back to John's original question. Instead of trying to think about this in terms of like, where did they start, where did they end, just follow the formula, and then you don't have to think about those things. You just do the end point, h of 2. Let me highlight what I'm talking about, this kind of thing. Like just plug in the last point, plug in the first point, and then the math and the signs will take care of itself. Right, so just make sure if you're just following this function, you don't really have to think about, for that formula, I mean, you don't have to think about positive or negatives. Okay. I'm going to set up the next thing. We won't really get into instantaneous rates of change today, but I would like to talk about the concept. And I just need to open up this web applet that I forgot to open up before. Just give me 1 second.
Professor, I can't hear you.
Yeah, I can't hear you.
Thank you. I accidentally clicked off my mic. So what I was trying to say is, in an instantaneous rate of change, we're thinking about at a specific instance, right? Think about the difference between these two things. Average was over a period, instantaneous at an instance. And so average, like we just looked at, is like the slope of a line. Well, with instantaneous rate of change, we want to be looking at a very specific point and what the rate of change is there. And so what that looks like, let me share my computer screen and show you this. Let me move it over here. Share this. The idea is, and let me go ahead and make this function look more like the picture we just drew a second ago. So let's flip it upside down. And that's fine. So the instantaneous rate of change would be, this is currently showing the average rate of change between A and B on this picture. Right, let me just make sure I'm showing what I think I'm showing. Yeah, so it's currently showing the average rate of change between these two things. And I can draw on this. This is average rate of change from A to B. Literally the picture we were just looking at before, right? You're connecting two dots. And you can slide this around a little bit and move the points, is what this applet lets you do. You can kind of move the points around. You can make them closer to each other or not. Now, the instantaneous rate of change, another way to say that is it's the slope of the tangent line. Now, even though this curve, the black curve looks curved, right? The graph function is obviously curved. If we zoom in close enough at a location, it'll look like a straight line. Right, so I'm just going to start zooming in on this graph. It still looks curved, right? But if I get close enough, it's going to start to look like a straight line. And so the idea is if you hone in really, really close at a spot, right? So right, one instance, it becomes straight. It's already looking very straight, and I'm not really even that close, right? The closer you get, sort of the straighter this thing is going to look. Let me just go ahead and refresh and get back to the original. And so that's what we're trying to do here. We're trying to measure the steepness of the line at a very specific spot. And it's given by a limit, because notice how as B, I'm going to shift this slider, and as B gets closer and closer to A, the blue line that connects them gets closer and closer to being the tangent line. In other words, if I zoom in on that spot again, if we move them kind of far away from each other, you get an average rate of change thing, right? But as this point B gets closer and closer to A, it essentially approximates the straightness of that line at that location, right? So I'm zooming in again, and you can see it's still doing an average rate of change between those things, but the blue and the black line are like right on top of each other because it's kind of approximating how curvy it is, right? And again, the idea is like if B gets closer and closer and closer, it eventually will approximate the exact steepness at that location. I'm going to switch back to my iPad in a second and show you the notes, the implications of this in the notes. But are there questions about what I'm trying to say from this applet before I switch back? So I'm just going to look at this in terms of the limit. So that's exactly what it says right here in terms of the exact value of this derivative, right? It's the limit as the 2 points get close to each other of the average value equation, right? This thing is just the average rate of change that we just looked at. That's the exact same formula, right? But the added thing is that we now have a limit associated with it, right? This is the new thing. And so when X approaches B, that's like the 2 points getting closer to each other. And then when it equals B, you end up with the slope of the tangent line, which tells us the steepness of the graph. Questions about what I'm trying to say there? I'm going to draw that picture on this one. I'm going to draw the picture that we just did a second ago right here. So we have this like upside down minus X squared kind of curve, right? And I'm going to try to recreate that picture I just did a second ago. And let me add a couple words before I do that. So this formula right here, this is a super important formula. I think I might throw a red box around it. Actually, it's that important. This is the exact value of the instantaneous rate of change for the function f of x at the point x equals b. And what I've explained it before is that we denote it with f with the apostrophe, right? So we call that the derivative at the point b. And I'm going to try to draw that picture we just drew a second ago as well. So wondering if there are questions. So far, so good. So in that applet we just saw a second ago, by the way, this is method 2, right? I'll talk about method 1 in just a second. Method 1 is just the estimate. I thought it would be helpful maybe to look at method 2 first. So in that applet, we cared about some point. I'm going to call that point B. And we wanted to know the tangent line at that point. And in order to get that, we do a limit as x approaches B. And so x approaching B might be down on the x-axis like this. Like here's x1, maybe this is x2, x3, right? These things are getting closer and closer to B. So what I'm trying to show down at the bottom here is this is the limit. This is going to be x approaching B right here. And the idea is we want the slope at that point that I'm circling right now, right? We want the slope of that tangent line. And in order to get that, we do a bunch of average rates of change and allow them to get closer and closer to B. So like the first one.
Could you scroll down just a little bit?
Is that good?
Yeah, that's good.
Right, so if x is far away from B, do this with these dotted lines here. It might be like connecting those two. And then as x gets closer and closer, the lines are just going to get closer and closer. Right, so this one might be like x2. Maybe x3 is right here. And ultimately, right, as x actually reaches B, we end up with that tangent line. So I'm doing that one in blue here. I make that one 100%. That's the one we really care about. We want the slope of the blue line. And so what I'm trying here is f prime of B tells the slope of the blue line. And we obtain it using this concept of a limit. It doesn't look great. Let me try to adjust that a little bit here. It's a little better. So I'm just trying to like draw what I just showed you in the applet, and I know it's kind of hard to do, but that's my best go at it. Can I answer a question about what I'm trying to say here? This is why we talked about these limit techniques, right? Because this thing's going to end up being indeterminate most of the time. We're going to try to calculate derivatives. That's going to end up being indeterminate, and we're going to have like techniques that we know how to solve it. I'm going to write down a few more things, do a few more clarifying thoughts here, but are there questions? Let people catch up writing questions about what I've said. So when people look at this function or this expression, they oftentimes get really confused when it's time to actually do stuff, right? So x is a variable, b is a number. And so f of b is also a number, right? And so it's important to realize those things when you're actually thinking about this. So I just like writing this stuff down because people get really confused. So f of x is just the function that we care about, right? And x is the variable. It's just x. F of b is f of x with x equals b plugged in. So it's a number. So we have like a function minus a number on the top. And then on the bottom, you have something similar too. B is also a number. V is a specific x value. And so again, I just think writing this stuff down will be helpful. Once we do an example next class, probably, you'll be able to look back at this and say, oh yeah, I see what you're saying now. And that's the kind of key point that is said sort of throughout, but really can't emphasize it enough, is that when you take the derivative of a function and you plug a point in, it'll tell us the slope of the tangent line. At f of b. And the way to think about that is it's thinking about how steep is the function there. It's a measurement of how steep is f of x at f of b. Slide up for those folks who need that. That's what I am trying to say. Now that's the exact method, as you can see, right? That's how we calculate these things exactly. That's what we really, really, really care about. And before we do it exactly, we're going to estimate it using the method right at the top there. But I thought it's just helpful to kind of see what we're actually building towards. Any questions about that? So the first way we're just going to estimate this thing then, right, we're still kind of thinking about f prime of b here, but we're actually doing two individual rates, average rates of change, right? So the two things I boxed in there are the average rate of change from A to B, the average rate of change from B to C, and then when you divide by 2, you're averaging the average rates of change. And so maybe I'll get more into this next time, because I want to spend the last 5 minutes doing something else. But the point is, this is the steepness. We're trying to estimate the steepness of the function of the specific point. We're going to talk about estimating it in class on Friday first. We sort of had the concept of doing it exactly, and then we'll look at some examples on this page.
Can you scroll up just for a minute? I wasn't done copying that.
Right here?
Yes, just a minute.
Sure. Yeah, so I'm going to stop here anyway and say something else. So while people are still writing that, the last 5 minutes I want to just spend mentioning attendance. You know, I started on Google Meet, I switched to Zoom, trying to figure out how to do this thing remotely, et cetera, et cetera. And I met with, I try to make a big deal about attending class and how people who don't attend this class specifically, it doesn't really matter to me whether people come. Like, it doesn't hurt my feelings if you don't come. What matters to me is that when people don't come, they end up struggling in the class. It ends up being a huge issue for that person and me, for that matter, because it's just a lot of work trying to catch up. And I really try to avoid those things. You just can't skip class in math class because every class builds on itself. So I really tried to emphasize that, and which is why I take attendance. Now, I've had a hard time taking attendance in Zoom. I've been trying to figure out how to do it automatically, and I'm gonna start doing it automatically next class. But what I need everyone to do in order to make that happen is I need you to register for that session. So I'm gonna put a link in the chat in a second. If you would click that link and please register for the course, not the course, I mean.
I
I
think
think I think I did that before I joined the meeting because it asked me for my name, email, and some stuff.
yeah,
And
me
it-
too.
Yeah,
it
it's
never,
standard.
it never
Me too.
Oh, okay, good. Yeah, I tried to change that, and I tried to test it out with myself, and I couldn't tell whether or not it was working. So did everyone do that? Did anyone not know what people are talking about? You should have been asked to enter your name and your email. Great. So what that's going to allow me to do is I'll be able to go in. It just takes attendance for me rather than me having to write down names or blah blah blah. And I'll be able to see like where cameras on and off, where who contributed, who typed things in the chat, when people came and left, etc. And it's honestly, it's less for people who are here right now because you guys are in class. It's more for people who either have their cameras off and I want to see are participating, or people who aren't here and I want to be able to follow up with those people and see whether or not they're keeping up. It's really important to me. All right, it just becomes a huge issue when people fall behind. And again, not because because people end up failing. That's what I really care about. So that's what I'm getting at. So I guess we don't need the last 5 minutes. If everyone registered, then great. I'll be able to check that out. And I'm going to reach out to everyone who wasn't in this chat. I'm going to reach out to people who have their camera off and just make sure that they understand that they're going to, if you don't participate in the course, then you're going to lose points. But I understand not everyone has a camera. So that's fine. Like I know I've talked to Janetta about this before. And I know Janetta asked questions today, and so I know she was here. That's all I'm asking. And anyone has a camera on, that's all I'm asking as well. So that's great. Okay, well, there are a couple minutes left. Does anyone have anything else they want to ask about? My iPad died. It didn't die, it just turned off. Is anyone all set with writing that down? Okay. I'm happy to go over number 7 too, if you're still interested, Simon.
I'm still interested.
Okay, I'm going to do that, but if people want to bounce out of here, that's fine too.
Adios.
Take care.
Thank you.
Yeah,
Thank you. Have a good one.
Bye. Oops, that's the wrong one. Yeah, this one it's probably trickier than it should be. So what are you thinking about this one, Simon? Any thoughts?
Sorry, I muted myself. At first I tried plugging in the limit and that didn't work because it's infinity. I thought maybe if it's a negative number, because the first one is a negative number and then the second one is a positive, that the infinities would like cancel each other out, but that doesn't make a whole lot of sense.
Yeah. One of them's being raised to the 8th and one's being cubed though. So the 8th one's really going to take over. I realize how this one's confusing in the context of what we were talking about. But it's just so there's a couple ways to think about it, I guess. It's a polynomial. So one thing is it's degree 8, right? It's got an x to the 8th, which means it's even. And we know that even degreed things has a -4 coefficient. And so it's going to be, I know that the ends are going to look like this then. They're both going to point down. I know I didn't have you in pre-calc last semester, but this is the kind of thing we talk about in pre-calc a little bit. Like if we know the degree of a function of a polynomial, then we kind of know what the ends are going to do. And so in other words, this left end just keeps going down, down, down. The right end keeps going down, down, down. And so there's no limit, just kind of thinking about what the graph looks like. In the context of rational functions, we could just make this over 1, and now it applies, now it's a rational function. And the degree in the numerator, that's probably the best way to think about it if we want to just use the notes that we have. right? This numerator has degree 8. The denominator has degree 0. And so what does this tell us in that case? The degree in the numerator is bigger. So this is n bigger than m. Simon?
Hold on, I'm looking at my notes.
Sure.
So then would if n is greater than m, then both limits are infinite?
Yeah. And I just mentioned they're both ends are pointing down, so they're both going to negative infinity because of the minus sign out front.
Ah, okay, I see. Thank you.
Sure. All right, I'm gonna log off, guys. I've got a meeting in a few minutes, so I will see everyone next time. Take care.